Scientists around the globe are telling us that we need to change our relationship with fossil fuels and that we need to change it now. So why haven't we already switched to renewable energy? Well, renewable energies are often intermittent. Take solar for example. Here in Manchester, we know very well that it isn't always sunny, so solar power is not always at its most efficient. This necessitates energy storage in the form of batteries. This means that during peak production times, excess renewable energy can be stored to then later be used to consolidate the supply during times when the production does not meet up with demand. The issue is that most energy storage focuses on lithium. Despite the fact that lithium is a limited resource, it's still used globally in millions of electronic devices ranging from mobile phones to electronic vehicles. This increase in demand has led to concerns over the future availability of lithium. But what can we use instead? Well, below lithium on the periodic table is an element that can also store energy. Not only is sodium cheaper than lithium, it's also far more abundant, so it is immediately beneficial from a sustainability perspective. Sodium-ion batteries are also safer. They are not prone to catching fire and can be safely shipped without the stringent regulations attached to lithium-ion batteries. They also use aluminium current collectors, which are both cheaper and lighter in weight than the copper ones required for lithium-ion batteries. So why aren't we already using this technology? Well, it's not fully optimised yet, which is where my research comes in. My research begins by synthesising a sodium-based layered oxide from earth-abundant precursors using a method that is simple and scalable. This is the key first step to producing a high-powered battery cathode. But these improvements can only take us so far, which is why my research moves on to focus on the lesser studied non-electrode factors of sodium-ion batteries. So during the charging and discharging of a battery, a protective layer forms in the anode. This is called the Solid Electrolyte Interphase layer, or the SEI layer. It is essential that we get a really thorough understanding of the formation of this layer, as if it were to form unevenly, it results in loss of capacity and ultimately the failure of the battery. Which is why I will be using advanced techniques such as X-ray Photoelectron Spectrometry to gain a really detailed insight into the composition of this layer. Not only can we reveal what's on the surface, but also the composition throughout the entire layer. This detailed information will allow us to tailor the formation of the SEI layer to result in the most optimised battery as possible. Once working with an industrial partner, I hope this work will contribute to the understanding of sodium-ion batteries, hopefully to commercialisation.